Hello everyone, in this video we are going to analyze simple harmonic motion using these equations and then look at analyzing them graphically. So these two equations will tell you where a object is when it's in its simple harmonic motion given the frequency, time since being released, and the amplitude. And so there's two different ones, and it's saying that if at time equals 0 it's released from the amplitude, and that's where the time starts, and you use cosine. If you start the timer when the object's at the equilibrium point, use sine. And so let's draw out what this is basically saying. So let's use a spring since it's probably the easiest to understand. So let's say you have an object and it's being stretched out and this is equilibrium, right? So this right here will be the amplitude. And let's say you release this block from rest at time equals 0. And then you let this box oscillate back and forth. Given the time, you can find what x position it is at relative to x equals 0 at equilibrium. And so then you would use this equation right here. And this is going to be the most common one to use, is releasing it from rest at the amplitude. But if you released it, let the box travel to equilibrium, and then started the time, then you would use this equation, which is used less often. Alright, so let's look at an example using these equations. So we have an object. An object's position is given by this equation. What is the object's amplitude, frequency, and period? Okay, and so we were given this equation, x equals 0.2 cosine 4 pi t. So since we're given this, we can use the equation that we know that has these variables in it. So we know that x equals the amplitude cosine of 2 pi frequency times time. So now we can pretty much just map these to each other, where this is the amplitude and then this is the 2 pi frequency right here. So let's go ahead and write these out. So the amplitude is the easiest one. It's just the coefficient in front of the cosine, so the amplitude equals 0.2. Okay, and then if we want to find the frequency, we know 2 pi frequency equals 4 pi. So the pi's will cancel and our frequency will just equal 2. And so that'll be our frequency. And then if we wanted the period, we know period is just 1 over frequency. So the period would be 1/2. Okay, so now let's look at how we can look at graphs between these. So we're given a position versus time graph as shown in simple harmonic motion. So we're going to find the graphs for velocity, acceleration, force, and then energies of the box. Okay, so let's first do velocity. So we have to think about what is going to be the velocity at different points. So I think the easiest way to do it is think about, well, it's at position 0. And so we're going to assume this has been oscillating before the graph started. It's not being released from rest necessarily, because this is the equilibrium position at x equals 0, right, over time. And so this position is x, so this is when it's at its amplitude over the course of time. So we're assuming it's not being released from rest, because if it was released from rest, it wouldn't start oscillating if it was started at the equilibrium. So it must start with some velocity, but we know places where the velocity will equal 0, and that's at the amplitudes. These are the amplitudes, and so this is where it switches direction. So the velocity must be 0 because we know the velocity is the slope of the position graph, and the slope at these points is 0. Okay, so now we can mark our 0 points. So we know the velocity will be 0 at each one of these points right here. Okay, so then when is the velocity going to be at its max and minimum? Well, we see that the velocity is, at this point, we know it's the slope. It's going to be positive here, negative here, positive here, and the slope is the greatest when it's at these points. So if we know it's the maximum here, and then it goes down to a minimum here, and then a maximum here, and then a minimum, and we can kind of see the pattern that the velocity is going to make. And so we can draw in our velocity curve here. using that information. And the reason the velocity goes negative is because it's going in a different direction, because the direction is, we'll say in the positive direction, we'll just have to define one of them as positive and then one as negative, and so that's how we can draw our velocity curve. So now let's think of the acceleration. So we can use the velocity graph to find acceleration, or we can use the position graph. So let's think about, when is the acceleration going to be 0? Well, the acceleration is 0 when the velocity is, when the slope of the velocity is 0. So right here the slope of the velocity is 0, right here the slope of the velocity is 0, and at each of these points the velocity slope is 0, which means the acceleration should be 0. But we also know that given a simple harmonic motion, at equilibrium the acceleration equals 0. So right here it's at equilibrium, right here it's at equilibrium, and they match up with where these points are. So we can use that to say, okay, the acceleration will be 0 right here, right here, and at each one of these points the acceleration is 0. So now, what is the acceleration going to be over this first time period? Well, we know it's going to be kind of like a curve here, but we see it starts off very little and hits a maximum right at this point. This is where the slope is at its max. So the maximum points are going to be here, and then the maximum in the positive is going to be here. And so we can go ahead and fill this in, and this will also be 0. And so our acceleration graph will look like this. And so now we have a graph of our acceleration. Now let's think about the force, and this is typically talking about the spring force, for example. But we know that the force is just going to be proportional to the acceleration, because if this is the only force and it's in simple harmonic motion, then this will be the only force. There's going to be no other force, so this is going to be proportional to the acceleration of the system. So it's going to follow the exact same trend of the acceleration that we just drew. Oops. Just imagine it's coming up here. So it'll follow the exact same as the force. So now we get to energies. Now we haven't actually talked about spring energies yet, but the kinetic energy is just going to be 1/2 mv squared. So we need to look at this velocity term, since that's what it's going to track with. So we see the velocity is going to be 0 at these points in the middle here. So we're going to want that also to be 0 for the kinetic energies. So we said they're 0 in the middle, so this is where the points of 0 are. But now, the kinetic energy is always positive since the velocity is squared. So we see that we have a max velocity at these points. At each one of these we have a max velocity. So those are going to be where the maximums are. So our maximum will be here, 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 and here. So now we can fill in this graph here and see that it's going to be still an oscillating graph, except for it's never going to go negative because the energy will never be negative. Okay, and so we now can find this potential energy. And even though we haven't even talked about what spring potential energy is, I'll write the equation just for sake. It's the K for spring times the x squared. So we could look at the position and do the same thing. See where the position is 0 and mark off where the positions are. So the position is 0 at each one of these points here. So we can find where it's 0, and it's at the max in the middle, which is the opposite of the kinetic energy, and that's the point that I'm trying to show here, is that the positions are going to be 0 where the kinetic energy is at a max, which is what the potential energy is saying, and in the max where the kinetic energy is 0. And so we can go ahead and fill this in. And so it's interesting, if we were to find, let's say, the energy total, this will just equal the kinetic energy plus the potential energy. And so if we were to put this on the graph, we would just see that it's a straight line where it does not lose energy because we have energy conserved at the peaks. And we could draw this on both of these graphs here. And so we see that the total energy does not change because these two are basically opposites of each other. Okay, so I hope that was helpful. Leave your questions down below, and thank you for watching.